Welcome, everyone, to the New York Combinatorial Seminar. Sudipta Mallik is giving a talk today, and Sudipta, the floor is yours. Thank you.
Thank you, Sandra. Thank you, other organizers, and for having me. And before I start my talk, that I would like to say that New York Combinatorial Seminar has a big community, and also I like watching your videos, YouTube videos. So because of this, I would like to talk about something which is not related to my talk. So I want to spend 1 minute, which is about um, this journal we started a few years ago. The American Journal of Combinatorics is a double-blind open access journal, and you can submit research article, notes, surveys in all branches of combinatorics and graph theory. So, and also there is no article processing charges. So you can ask your, let your colleagues, students know about it. And also in the future we would need editors for different subject area in combinatorics and graph theory. So if you are interested in doing editorial work in the future, please let us know. And if you have any question regarding this journal, you'll have time at the end to ask me. All right, now I can happily start my actual talk. So the main idea about my talk is, the relation between matrices, linear algebra as broad, and graph theory. So you can associate matrix with graphs, and also graphs can be associated with a given matrix. So I'll talk about that a little bit before going to the Moore-Penrose aspect of the talk. So let's start with a graph, simple graph on n vertices, 1 through n, and m edges. Now we define a vertex edge incidence matrix, G of G. The incidence matrix is denoted by M, and it has n rows and m columns. So the rows are indexed by the vertices, and the columns of incidence matrix are indexed by the edges. So the ijth entry of the incidence matrix is 1 if vertex I is incident with edge ej, and 0 otherwise. I'll give you an example. And an important property of incidence matrix is if you multiply m times m transpose, you'll get the degree matrix plus the adjacency matrix. So I'll come back to that later. So here's a quick example. So you can see the graph on 4 vertices and 4 edges. So this is a 4 by 4 matrix because the rows are indexed by the vertices and columns are indexed by the edges. So an easy way to look at incidence matrix is to look at it column by column. So because each column has exactly 2 ones, everything else is 0. So if you look at edge 1 is, see if I can do this. Is it? Huh. I should have used this before. What's happening? Okay. Huh. So give me a second. I thought I can use my pen, but seems like it's not working. All right, anyway, I'll move on. So if you look at age 1, so age 1 is between vertex 3 and vertex 4. So the 3, 4 entries of column 1 are 1. Similarly, if you look at age 2, age 2 is between vertices 2 and 3. So 2, 3 entries of column 2 are 1, everything else is 0. So we write this incident matrix column by column, so that would be easier to write. So now for this incidence matrix, you can take inverse. So I already have taken the inverse, and inverse, you can guess that rows are indexed by edges and the columns are indexed um, by the vertices. Now, if you look at it and see that this has bunch of 1/2, -1/2, and 1 and 0, and if you look at these entries and try to guess what are these entries saying regarding the graph. So I'll give you a second to think about it. Maybe look at in edge 1. Edge 1 corresponds to the first row of M inverse. And you can see that the entries are 1/2 and -1/2, right? So not sure what the sign is saying, but if you try to understand the pattern, you can see that the edges that are on the cycle, edge 1, edge 2, and edge 4, they are, row 1, 2, and 4, their entries are 1/2 and -1/2, right? And the edge that is not on the cycle, edge 3, the entries are 1 or 0, right? So it's saying something. So now we have to come up with a combinatorial formula for the entries of M inverse, right? So we have this formula. We published that in 2021 in Discrete Math. And this is a work with one of my undergraduate, and he was a graduate student, Ryan Hazard. So the result is this. If you have odd unicyclic graph, that means the graph has exactly one cycle, and the cycle is an odd cycle. Then if you take incidence matrix, the incidence matrix is invertible, and is inverse are given by this formula. So the ijth entry of the M inverse is given by this formula. So if you look at this, if edge EI is in the cycle, so the ijth entry is going to be -1 to the distance between edge EI and vertex J divided by 2. So if you go back, so if you look at 1, 2 entry, or maybe, I don't know, 1, 4 entry, 1, 4 entry means you're looking at edge 1 and vertex 4. So the distance is 1 because probably that's not a good example. So maybe you can do 1, 2 entry. So edge 1 and vertex 2. So the distance is 1 because there is a 1 edge between the edge 1 and vertex 2. So you have -1 to the power 1 and divided by 2. That's why you have -1/2 in the 1, 2 entry. So that's this formula is saying. And if the edge is not in the cycle and the vertex is in the graph, where if you delete the edge EI and then look at if the vertex J is in the part where the cycle is, then the entry is 0, and so on. So this is the combinatorial expression for the inverse of the incidence matrix. Now let's look at another example. So the last one had 4 edges. Suppose I delete the edge 4. So if you delete edge 4, you get a tree. Tree means is a connected acyclic graph. Doesn't mean a connected graph that doesn't have cycle. In particular, this is a path and 4 vertices. So since I deleted edge 4, so I got rid of column 4. So then you have this matrix. Now, if you find inverse of this, so what would the entries of the M inverse say about the graph? Probably, you notice that matrix is not square. Probably you're thinking I'm high. So not quite. So there is something called generalized inverse of any given matrix. It doesn't have to be square matrix. So if you have M by N real matrix, and then is generalized inverse is called Moore-Penrose inverse. is denoted by A plus or A dagger. So A dagger sounds a little bit violent, so I'll call it A plus. And it was done long time ago, actually. In 1920s, E.H. Moore, first introduced that. And E.H. Moore is my great, 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 great mathematical grandfather. And also it was independently done in 1955 by Roger Penrose. He was a student back then. And he came up with the same idea. If you remember, Roger Penrose got a Nobel Prize 4 years ago. So that's why it's called Moore-Penrose inverse. And before I talk about its combinatorial properties, I want to spend a little bit time about this interesting inverse. And you notice that I said the Moore-Penrose inverse, which means the inverse is unique. And if you have a real matrix or even complex matrix, the inverse is unique. And how do you find that inverse? So if you have m by n matrix A, Moore-Penrose inverse A plus would be an n by m matrix that satisfies these 4 equations. So I'm not going to say this 4 equation. You can look at the equations. And obviously, if A is invertible, then A plus is going to be A minus. That's why it's called generalized inverse. Okay. Now, I'll just say there are a lot of nice properties about this A plus, but I want to mention that one property. So we solve Ax equals B, this matrix equation a lot. So if A is an m by m matrix, B is a m-dimensional vector, we are solving Ax equals B, solving for X, right? So from basic linear algebra that if you might have a solution, infinitely many solution, or unique solution, or no solution, right? So if it has infinitely many solution, then you want to know the least square solution, right? So think about geometrically. So solving Ax equals B means what? We are looking at the column space of A. Geometrically is the hyperplane going through the origin, and you want to know the vector B is as a point is in that hyperplane or not. So if B is in the hyperplane, Ax equals B has a solution. If B is not in that hyperplane of column space of A, there is no solution of Ax equals B. So if there is no solution, you want to find a point in the hyperplane which is closest to this point B. And you know that that's a least square solution or orthogonal projection, and that is given by this A plus B. So A plus B is the Moore-Penrose inverse of A times B. And in technically, that gives you the least Euclidean distance from B. So if you look at Ax equal Ax and minus B, so you can see that A times A plus B minus B is Euclidean norm. Norm 2 norm is the smallest among all the Ax equals Ax minus B their norm. So this is A plus B gives you the least square solution. So this is really a nice application of Moore-Penrose inverse. All right, so now let's go back to the old question. If you have this matrix, not square matrix M, or incidence matrix of this graph, what would be M plus? I'm not calling M inverse anymore because now you know what Moore-Penrose inverse is. So what would be M plus? And now what would the entries of M plus say about the graph structure? So that we want to know. So I have the calculation. You can find M plus easily, and then this is given on the right of the screen. Now edges, the rows of M plus are indexed by the edges, columns of M plus are indexed by the vertices. So now look at the entries and try to think about what are they saying about the graph. For example, you see that 1/4 is a common factor, 1/4. So what is this 4 saying about the graph? 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 4 saying about the grap It's not hard to see that the 4 is representing, guessing, if you guess, 4 is representing the number of vertices, right? Now, if you look at some other entries, maybe you look at, 1-3 entry of M plus. So 1-3 entry of M plus, I wish I could write. Anyway, so 1-3 entry of M plus is 1, right? So, and what does that mean in terms of the graph? So if you look at the graph, if you delete edge 1, then you have two connected components, right? One side has 3 vertices, other side has 1 vertex, right? So if you delete edge 1, vertex 3 is one side of the graph. Now look at the other side. Other side has 1 vertex, right? So that's why edge 1-3 entry of M plus is 1. Now if you look at 1-4 entry of M plus, which is 3. So if you delete edge 1, and then vertex 4 is one side of that edge, the other side has 3 vertices. So that's why 1-4 entry is 3. So I call this theorem as look at the other side. So when you delete an edge, look at the vertex and look at the other side of the other side of the graph and see how many vertices are there. Okay, so again, this is just an example, and I like to prove everything by example. That's my favorite technique of proving anything. that was supposed to be a joke. Anyway, so if you look at a tree and it has n vertices and n minus 1 edges, and you can find M plus. So M plus is given by this formula. So if you look at the ijth entry, so you look at edge EI. So if you delete edge EI, there are two components. One is, like, you call it head part, other side is the tail components, head component and tail component. If J is in the head component, then the ijth entry would have the number of vertices in the tail component. And similarly, if J is in the tail component, then the ijth entry is the size of the head component. I mean, number of vertices in the of the head component. And the sign was not clear. The sign is given by -1 to the distance between edge EI and vertex J. So if you go back, you see that 2-4 entry is -2, right? So 2-4 entry is -2 means what? You delete edge 2 and then distance from vertex 4, which is 1, right? Then you have -1 to the power 1. That's why you have the sign negative. And if you delete edge 2, one side has 2 vertices, other side has 2 vertices, and 4 is one side. We can call it the head side. Then the entry would be the number of vertices in the tail side. So look at the other way, other side. So this is the theorem, which was published in 2021 in discrete math. So again, the proof would be really long because you have to show that this matrix M plus satisfies those 4 properties. Now let's move on. Let's get another example. So this is not a tree anymore. This is an unicyclic graph. Actually, even unicyclic graph. It has one cycle, which is even cycle. So now if you look at, let's say, 4-3 entry of M plus. So just looking at the graph, can you tell me what 4-3 entry would be? 4-3 entry means you are looking at edge 4 and vertex 3. Not hard. If you just think about, if you delete edge 4, you have 2 components, and 3 is one side of the component, and look at the other side. It's like, again, look at the other side, that theorem. So if you look at delete edge 4, 3 is on the right side, and then the left side has 6 vertices. So it would be in terms of 6, right? And then you divide by the number of vertices, and then the distance, the negative sign is coming from -1 to the distance between edge 4 and 3. Edge 4 and 3 distance is 1, so that's why -1 to the 1. Similarly, you can do edge 4-6 entry, then you delete edge 4. Now look at 6 vertex is on the left component, so then it would be in terms of the number of vertices on the right component. which is 3. So this is still like, like the tree case. If you delete the edge and look at the other component. But if you take the edge on the cycle, things are really, really complicated. It's not, the answer is not easy. So I'll show you the answer. So this was published in 2022. So the first 2 lines of the ijth entry you can see, which I just explained, like the tree case. But if the edge is in the cycle, then the answer, the combinatorial expression of the ijth entry is much more complicated. And I don't want to explain that what it is, but I just wanted to show you this to emphasize that things can get really messy really quickly. And it's not easy to come up with the combinatorial expression, even for this easy case, unicyclic graph. All right, so the question is there any general strategy to find M plus, Moore-Penrose inverse of the incidence matrix? And luckily, we have a theorem that's a little bit helpful when you find M plus. So if you have a connected graph, G, and incidence matrix M, so there are 2 cases. When G has an odd cycle, then M times M plus would be an identity matrix. And if G does not have odd cycles, which means G is a bipartite graph, then M plus is going to be identity matrix minus 1 over n times a square matrix whose ijth entry is -1 to the distance between vertex I and j. And this is a nice theorem, and usually in a good talk we should at least talk about one proof. So since this theorem is really nice, I'll show you a quick proof of this theorem, and then we can talk about other things. So let's try to prove this. So you remember that you had 4 properties, M plus satisfying 4 equations. So one of the equations would be this: M times M plus times M would be M. So if you subtract M plus M from both sides, then you get this identity minus M plus times M is 0 matrix. So now we want to know what are the rows of this matrix identity minus M plus. Suppose the row is x1, x2, xn is a row of this identity minus M plus. So if you multiply that row with M, you get a 0 vector. And that means, and remember that each column of M has exactly two ones, everything else is 0. And these 2 ones are corresponding to an edge. So if you have an edge, ij, then xi plus xj would be 0. And this is true for all edges ij. So that means xi equals negative xj for any edge. But then if you have a path, you can repeatedly apply this process. And then if there is a path between vertex I and j of length d, then xi is -1 to the d times xj. So this is generally true. Now we are talking about 2 cases. First case is that C, so we're calling the cycle, if there is an odd cycle, I'm calling that odd cycle is C, and take 2 vertices I and j on that cycle. So since this is an odd cycle and vertices I and j on the cycle, so there exist paths of odd length and even length between I and j, which means xi equals negative xj if you look at the odd path between xi and xj, and xi equals xj if you look at the even path between xi and xj. So if you solve xi equals negative xj, xi equals xj, which, really hard equation to solve. So xi equals 0, xj equals 0. So that means we prove that if you look at any vertices, or any vertex I on the cycle, corresponding xi would be 0. Now, this graph is a connected graph. That means there is a path between any two vertices. So if you take any vertex not in the cycle, there is a path from that vertex to a vertex on the cycle, which implies that all entries xi, x1, x2, xn, all of them are zero. So we prove that the row is zero row, which means each row of identity minus mm plus is zero matrix, which implies mm plus is identity. Now let's move on to case case B. So suppose G has no odd cycle. So if it does not have odd cycles, or it is a bipartite graph, so lengths between the paths between any two fixed vertices either odd, either all odd or all even. And you can see why that is the case, because if you have odd path and even path between two vertices, then you can make a odd cycle. So that's not the case. So if you look at paths between any two vertices, either all paths are odd or all paths are even. So based on that, if you fix a vertex I, now look at any vertex V, so xv is going to be -1 to the distance between I and V times xi, which means x1 through xn can be written in terms of xi. So the x1 through xn becomes xi times the first entry is -1 to the distance between I and 1, second entry would be -1 to the distance between I and 2, and so on. Now we have to figure out what that xi is. So if you use the another equation of this Moore-Penrose inverse, m plus m times m plus is m plus, and if you use the symmetry of m plus, you can show that xi is going to be 1 over n. So we prove that ijth entry of identity minus m plus is going to be -1 to the distance between I and j divided by n. So that completes the proof. It's a nice, easy proof, to talk about. So that's why I chose this proof to present. Now remember that we have a general idea, but still if you want to find m plus of incidence matrix M, things may not be easy. But sometimes if the graph is well structured, the answer may be nice and algebraically nice also. So I had an undergraduate student, Jared Ibsen. So he wanted to do some research. So I gave him this wheel graph. And the nice thing about wheel graph is you can write the incidence matrix as this block matrix, where the 2-2 block is a C. C would be a circular matrix with first row 1, 0, 0, 0, 0, 1. And then if you find its inverse, M plus is going to be also a nice matrix, algebraically nice, where you can see that it has nice block matrix, and this x1 2 block is x, which is going to be a nice circular matrix given by this formula, and then 2 2 block is y, that is going to be another nice circular matrix. So if you look at an example, this is a wheel on 4 vertices, and you can see that incidence matrix, the 2-2 block of the incidence matrix is a circular matrix with first row is 1, 0, 1. If you don't know circular matrix, it's very easy to explain. Circular matrix, if you look at the first row and then for the second row, you shift that first row to the right. So 1, 0, 1, if you shift to right, then it'd be 1, 1, 0. Then for third row, you shift again to the right, it'd be 0, 1, 1. So that's the circular matrix. And if you find M plus, and you look at that in a 2-2 block of M plus, or if you look at 1-2 block, those are also circular matrix. So this was a nice results for wheel graph. But there are a lot of graph classes you can consider. So if you have undergraduate students, if you want to do a quick undergraduate project, you can pick a particular graph, maybe Peterson graph or Fullerene. You can find Moore-Penrose inverse of their incidence matrix. If you want a challenging problem for your undergraduate or maybe even graduate, you can choose a class of graphs, for example, bicyclic graph or cacti, and then you find a combinatorial formula for the entries of M plus, the Moore-Penrose inverse of its incidence matrix. And things may not be, as easy as you think. So things get quickly complicated. But these are nice undergraduate project you can pursue if you want to. There are a lot of open problems. You can find the two ways you can do. Either you can do combinatorial expression of m plus, or you can do algebraic expression of m plus if the graph is well structured. And then I'll move on to something else. I've been talking about incidence matrix. Now I'll talk about signless Laplacian. So signless Laplacian Q is degree matrix plus the adjacency matrix. So if you look at this graph is a PAW graph. Graph theorists are really, imaginary, like imaginative. You can think about a paw, right? So that's why it's called paw graph. So if you look at the degrees, the diagonals of the signless Laplacian, that is the degree metric. So degree of vertex 1 is 1, vertex 2 is 3, vertex 3 is 2, and vertex 4 is 2. So those are the degrees, 1, 3, 2, 2. That is the diagonal of the signless Laplacian. And then you add that to adjacency matrix. So that's how you get signless Laplacian. Why is it called signless Laplacian? Because if you do degree minus adjacency matrix, then you get Laplacian. An interesting property of signless Laplacian is you can get it from incidence matrix M. If you multiply M times M transpose, you get the signless Laplacian. So there is a connection with incidence matrix. Now, if you have signless Laplacian, I can ask the same old question. How do you find the Moore-Penrose inverse of Q, the signless Laplacian? And you can use properties of M, because if you do Q plus, that is M transpose plus. And if you use properties of Moore-Penrose inverse, it would be M plus transpose times M plus. And if you know the combinatorial formulas for M plus, then you have a summation formula for Q plus. But things can get really messy. And I want to show you one example. So one example is for tree. So if you take signless Laplacian of tree, Q, and the ijth entry is given by this formula. This is a combinatorial formula. So ijth entry of Q plus is going to be -1 to the distance between I vertex n and j divided by n squared, and then this summation formula. For each this summation formula, you have to look at the edges. So maybe I'll explain this by an example. So this is the old example, path on 4 vertices. So the Q, the signless Laplacian, is degree matrix plus the adjacency matrix. And if you find Q plus, and you get this formula, 1/16 times this. So now, for example, you can see that 1/16, what that means. We'll go back, you have n squared at the bottom, right? So the 16 is just number of vertices squared. That's why you have 1/16. Now, if you look at, let's say, 1, 3 entry. So if you look at 1, 3 entry, that means you are talking about vertex 1 and vertex 3. Okay. Now look at all the edges. So first, if you look at edge 1, so if you delete edge 1, and then you look at if you delete edge 1, then you look at the tail component. So usually I'm calling it tail component. If you have edge 3, 4, 3 is less than 4, so I'm calling the component. If you delete edge 1, then the component with vertex 3, it would be tail component, and the other component which has vertex 4, that's the head component. So if you look at so 3 is in the tail component. So now you have to look at the head component. So head component has 1 vertex, so you have to take 1 squared. Now if you look at H2 and H3, that's between vertex H2 and H3 are between in the path between vertices 1 and 3. So you have to subtract that. So if you look at H2, if you delete H2, then there are 2 components. One side has 2 vertices, other side has 2 vertices. So you multiply 2 times 2. And if you look at H3, if you delete H3, one side has 1 one vertex, other side has 3 vertices, so you subtract 1 times 3. So that's how you get -6/16. So that's a combinatorial interpretation of the 1-3 entry of the signless Laplacian of this path on 4 vertices. Now, this is all about graphs, and these are published. These papers are published. Then I got an email from Tom. You can guess what he was talking about. Obviously, he's talking about sign graphs. And in case you don't know who Tom is really well known for his work on sign graphs. So he emailed me and said that, okay, I saw your papers. These are, and I'm wondering if there are similar results for sign graphs. And I had no idea what would be similar result for sign graphs. So I started working on that. And then I got some results. Then things started getting complicated. And then I had two nice collaborators. They're brilliant mathematician, Melisha Angelique and Abdullah Alezemi. So we worked with them. So we got some nice results. So I'm going to explain some of the nice results we got. But before we go there, if you don't know what sign graph is, I'll give you a little bit background. So a sign graph is a graph in which each of its edges is positive or negative. So that means each edge has sign, positive sign or negative sign. So you can think about in the graph, we call it friendship graph, right? If there is an edge between vertex I and j, then if there's a friend, if you know or you don't know, acquaintance graph. But here you can think about like you know somebody, but either you know as a friend or an enemy, friend or foe. So if you know as friend is a positive edge, if you know as enemy is a negative edge. So knowing has qualitative importance here. So each edge has a sign. The sign of EJ is positive if EJ is a positive edge, and negative is a negative edge. So we write sign graph as G comma sigma. So G is the underlying graph and sigma is the signature or the sign of the edges. So I'll give you a quick example. Look at this graph. This is a sign graph. It's just a graph, but now we said which edges are positive and which edges are negative. So we can see that 1, 2 edge is positive, 2, 3 is negative, 2, 4 edge is negative, 3, 4 edge is positive. So we assign the sign of for these edges. So this is an example of sign graph. Now, the important concept in sign graph is called balanced or unbalanced. So if you look at a cycle in a sign graph, if the cycle has even number of negative edges, that means if you multiply the weights or the signs of the edges of the cycle, it's going to be positive. So then we call the cycle as a positive cycle or balanced cycle. And the sign graph gamma is balanced if all cycles in that graph are balanced or positive. All the cycles are positive. Otherwise, it's called unbalanced. It has other couple of characterizations. So I'll mention that later. So if you look at this graph, these are really trivial example. So if you look at the left graph, so this is a unicyclic graph. You have one cycle to worry about. So if you look at the cycle on the left, you have two negative edges, right? So if you multiply the signs, it would be negatives times positive. So the sign of the cycle is positive. It has one cycle. So all the cycles are positive. So the left graph is a balanced graph. And if you look at the graph on the right, look at the cycle. You have one negative edge, two positive edges. So if you multiply the signs, you'll get negative. So you have a negative cycle. So that means the graph is unbalanced. So now how do you define adjacency matrix? So it's like the way you normally define adjacency matrix, but you have to consider the sign. So ijth entry of the adjacency matrix would be positive one if the edge ij is a positive edge. The negative, it would be negative one if the edge ij is a negative edge, or zero otherwise. And then how do you define Laplacian matrix of the sign graph? So you take the degree matrix of the underlying graph of this sign graph, and then minus the adjacency matrix of the sign graph. So that's how you get Laplacian matrix. So interesting property of this Laplacian matrix of a sign graph is you can write L as n times n transpose or any incidence matrix n of the sign graph gamma. But the interesting thing here, there are multiple ways you can define incidence matrix for this gamma. So if you have n vertices, m edges, so incidence matrix is n by m matrix, same as the old case. The rows are indexed by vertices, columns are indexed by edges, and each column has exactly two non-zero entries, either 1 or -1. So if you look at edge, if you look at ik entry, so if you look at column k, which is corresponding to edge k, if edge k is between vertex I and j, if that's a positive edge, if that's a negative edge, then the ik entry and jk entry would be both equal, either both positive one or both negative one. Two choices. And if the ijth entry is positive edge, then the nik is negative of njk. That means nik and njk have opposite sign. But again, they're 1 or -1. So there are two choices there too. So because of these choices, you have a lot of different choices for the incidence matrix. I'll give you an example. So look at this sign graph. And if you look at edge 1 is a negative edge. So if you look at column 1 of the first incidence matrix, it is between the 3 and 4. So the 3, 4 entries are going to be equal because this is a negative edge. So you can write both 1 or both -1. Similarly, if you look at edge 2, that's also a negative edge. So it's between 2 and 3. So the 2, 3 entry of column 2 are going to be of the same sign. In this case, I chose both -1. And if you look at edge 3 is a positive edge. So it's between 1 and 2. So the 1, 2 entries of column 3 have opposite signs. And one would be 1, the other would be -1. So you have two choices. And if you look at the second incidence matrix, I kind of choose differently there. So there are many choices for each column. You have two choices. So you can multiply each column by a negative sign. You can get another choice. So because of these multiple choices, things are complicated. So if you look at an example, like if you have a graph that has all negative edges, so then if you take the incidence matrix of the underlying graph, that would be an incidence matrix of the sign graph. And if you take negative of the incidence matrix of the underlying graph, that is also an incidence matrix of the sign graph. So what we did, so in this sense, the sign graph is really a generalization of the graph. And we did all the results for graphs. Now, you have a lot of different choices for incidence matrix. Now, if you take Moore-Penrose inverse of the incidence matrix, things are getting really complicated. So, but before we go there, I want to talk about a matrix which I define, which is be useful in a couple of slides. So I named it path sign matrix because in the literature I didn't see any such thing. So I just named it path sign matrix. Path sign matrix for a connected balanced sign graph. I should have written sign graph. Anyway, so this is a n by n matrix whose the diagonals are all 1. So since it is a balanced graph, so another characterization of balanced graph would be, if you look at connected balanced graph, that if you look at any two vertices, so all the edges, all the paths between any two vertices, either all all positive or all negative. Positive path means if you look at a path and multiply the signs of the edges on that path, so that is positive. So this is a nice property of characterization of balanced graph is if you look at path between any two vertices, either all paths are positive or all paths are negative. So if you have a positive path between vertex I and j, then the ijth entry is 1. If you have a negative path, then ijth entry is -1. So I call this matrix the path sign matrix. And here is an example. The four vertices is a 4x4 matrix. If you look at one, the diagonals are 1. If you look at 1, 2 entry, the path between 1 and 2 is a positive edge. So sign 1, 2 entry is positive. If you look at between 1 and 3, the path is negatives times positive, positive times negative, right? So the path is a negative path. Actually, any path between 1 and 3 would be negative. So that's why 1, 3 entry is negative, and so on. So this is I call it path sign matrix. Now, this is a result we got that if you get a connected sign graph and n is an incidence matrix, so there are two cases. If the sign graph is unbalanced, then n times n plus is going to be identity matrix. If you remember, we had similar result before for graph that has odd cycle. And the second case is if the graph is a balanced graph, balanced sign graph, then n times n plus is going to be identity minus 1 over n times the path sign matrix I just defined. And the proof would be similar, but here we are using the concept of balance. And we did this last year. The paper is under review now. But still, it does not help us to find the combinatorial interpretation of the entries of n plus. And as I mentioned before, there are multiple choices for n, or even given a sign graph. So things are messy, not easy. So, but my collaborators are really good. We come up with a result for sign tree. You can see that it's getting complicated. But if you remember what the result we had for just normal tree, unsigned tree, it has similar kind of result, right? Look at the other way. Remember, if you delete edge, there are two components. One side has vertex j. Look at the other side. So it has that connection, but it has bunch of other things. Like for example, if you look at the sign between edge I and j, that matters. Then this W of EI, that's kind of weight, you can call it. That if the edge EI is a negative edge and both ends are negative, that means that if you look at the columns of edge EI, and that both are negative ones. So W of EI is -1, otherwise is 1. And also we have to take care of the sign of the edge, sigma of EI. So a bunch of things need to be considered. So I'll give you an example. If you look at the sign tree, so this tree is a smallest asymmetric tree, and I randomly chose positive or negative edges. So maybe look at the left side, edge 5 between 6 and 3, and we want to know that row 5, which corresponds to edge 5. So if you look at 5 for entries, that means you are looking at 5 for entry of n plus. And if you look at it, 5 for entry is -1/7. But why is it -1/7? I'm going to explain that. So 5 for entry means you're looking at edge 4, edge 5, sorry, and vertex 4, right? So now is negative times sign of the path between edge 5 and 4. If you go back, edge 5 and 4, that means you're looking at the sign of the path between vertex 3 and 4, which is positive times negative times positive, right? So it's the positive sign of the path. And W of E5, so if you look at the fifth column of incidence matrix, you see that those are both negative. So this W of E5 is -1. Then sine of E5, so E5 is a negative edge. So that's why sine of E5 is -1. And then what would be this fourth entry? So vertex, if you delete edge 5, there are two components. 4 is on one side. So look at the other side. So the other side has only one vertex, which is 6. So that's why you have this last positive one. And you divide by n, so that's how you get -1/7. So this is an example of combinatorial interpretation of the entries of n plus when the sign graph is a sign tree. But if you take different graph classes, so if you take unbalanced unicyclic graph, then you can prove that the incidence matrix is going to be invertible and its entries has some combinatorial interpretation. And if you remember what you did for cycle before, unsigned cycle, it has connection to that. So probably I'm not going to mention all of them. So maybe I'll choose one example. Look at, this is unbalanced unicyclic graph, because remember unbalanced means if you look at the cycle is a negative edge here, negative cycle. So not all cycles are positive, so it's unbalanced. So now if you look at the one true entry, so I choose this incidence matrix. This is just one choice of several choices of incidence matrices. So if you look at the 1, 2 entry of the n inverse, is going to be -1/2. But why is that true? Because you have to look at weight of edge E1. So E1 has both -1. If you look at edge 1, the first column of n, both are -1. So weight of E1 is -1. Then 1/2 times sine between the path from vertex 2 and the edge of the tail of edge E1. So if you look at edge E1, so 4 is the head, 3 is tail. So the distance between 3 and 2. So there's only one edge, which is a positive edge. So the sign of this edge is +1. That's how you get -1 times 1/2 times 1, you get -1/2. So this is just one example of combinatorial interpretation. And then this is a big general results. So if you have a connected sign graph, no matter balanced or unbalanced, because you'll have two cases, then if you take any incidence matrix n, we have a combinatorial formula for the entries of n plus. So this is a big result. I have 2 slides. So I'll start with the first slide. So the case one is if gamma is balanced. Okay. If the gamma is balanced, then ijth entry plus n plus is going to be the summation. So before you look at the summation, you see that entry is 1/tau of gamma. This tau is the number of spanning trees of the sign graph or the underlying graph. And what is this summation doing? So the summation goes over all the spanning trees T of gamma that contains the edge EI. So if you look at the ijth entry of n plus, so look at the summation where the summation goes over all the spanning trees T that contains the edge EI. Now look at the part of the incidence matrix that corresponds to that tree, spanning tree T. Now we already know how to find is ijth entry from a signed tree. So we use this formula. You have already seen this formula before. So we find the ijth entry of n plus corresponding to that spanning tree containing AGI. We have a formula for this, and we can do for all spanning trees of this balanced sign graph that contains AGI. And this is a combinatorial formula, but still, things are not clear. If you want to do for particular class of balanced sign graph, you have to have more precise formula, which may not be easy. That's why there are a lot of open problems you can work on. And second case is if gamma is unbalanced sign graph, then the ijth entry of n plus is going to be also a summation over all spanning TU subgraph. Now, what is TU subgraph? TU subgraph means is a subgraph whose connected components are either sign trees or unbalanced unicyclic graph. So in this case, we only look at H, which is a spanning subgraph on n edges that consists of unbalanced unicyclic graphs. So each component of H is unbalanced unicyclic graph. And C of H stands for the how many unbalanced unicyclic graph you have. And then in the summation, you have 4 to the number of unicyclic graphs, unbalanced unicyclic graph in H. And then you have to look at the part of the incidence matrix corresponds to H, which is going to be invertible. And then the ijth entry of that part submatrix, we already know how to find the ijth entry because we already worked on the ijth entry of the inverse when the graph is unbalanced unicyclic graph. So you already have seen this result before. And again, this is going to be a summation formula. But if you want to work on a particular class of unbalanced sign graph, things would be probably nicer if you can come up with some good combinatorial formula. Just I didn't want to give you an example for this. This is already really complicated, but at least I hope that I gave you some of the results where the entries of the matrices, Moore-Penrose of matrices, especially incidence matrix, they have some combinatorial interpretation. But there are a lot more things to do. If you are interested in working on some of the open problems, feel free to contact me, or you can give some easy problem to your undergraduate students. So there are a lot of things you can work on in this area. Thank you. If you have any questions, I'm here.
Thank you. That was very good, Sudipta. I'll stop the recording and we'll take questions.